We have a fantastic reset opportunity. I think COVID's been one of those events in the world, a bit like 9/11 or Kennedy's assassination. Not that I remember that, but one of these generation-defining events. And I think we're starting to see a rapid transition. We're seeing it in government. It's quite remarkable the number of things that they've announced in the last 12 months and the amount of cheques that they're prepared to write is absolutely staggering. But I think we're starting to see the benefits in the community, and I think that will only get better. We're also seeing it in the business community. I mean, we're seeing it here. Pretty much all the exhibitors that we have here and all the ones that I spoke to are actually flat out. They're all in the sustainability space. They all are passionate about their businesses, and they are all absolutely flat out. And that's not the story we hear from everywhere. So I'm just grateful for that we have that on the coast. But I think a switch has flicked, and the opportunities in the future are becoming terribly exciting. And that's part of the reason that I really love what Carel's business do, because it answers a very big problem that we have. But I don't need to talk about it. I'll throw you over to Carel.
For 100 years at least, humans will need the energy and chemicals traditionally found in fossil oil. But what if oil could be renewable, sustainable, and reduce waste in the process? This is the vision of Licella, a bridge to a lower carbon future. For almost 10 years, Licella's pilot facility near Sydney, Australia, has been pioneering the field of hydrothermal upgrading and developed a remarkable and versatile platform called the Catalytic Hydrothermal Reactor, or CAT-HTR. This patented technology converts feedstocks, including biomass residue and purpose-grown energy crops, end-of-life plastics, lignite, and used lube oil into synthetic crude oil, biocrude, and valuable chemicals.
In the CAT-HTR process, we're using water at high pressure and high temperature.
So we sort of copy and mimic nature. But what nature would take 200 million years to do, we do in 20 minutes. Biomass has been converted to biocrudes for many years using techniques like pyrolysis. The problem with that is it's unstable. Using catalytic hydrothermal upgrading with water as the agent of change, we can create stable biocrude that can ship, is not acidic, and is compatible to blend with fossil oil in a conventional refinery. That's the breakthrough.
One of the key differentiators of our process is that we do something amazing. We take the hydrogen from the water, and that hydrogen ends up in our product. We do not need to have external hydrogen added, which is a major, major bonus and advantage over every other similar process. We save a lot of costs, we save a lot of plant complexity, and we save a huge amount of greenhouse gases.
Here's how it works. A feedstock is processed into a powdered form, then mixed with water to create a slurry. The slurry is heated and highly pressurized. It then enters the CAT-HTR reactors, where chemical transformations take place.
The water hydrolyzes the biomass, it cuts it to pieces like the scissors. We are removing the oxygen as carbon dioxide, and we are taking some of the hydrogen in the water and move that into our product oil.
After about 20 minutes, the reaction is complete. Pressure is released, byproducts are separated, and heat is recycled. The results are valuable chemicals and oil, suitable for immediate use or blending in existing refineries. In the UK, a joint venture with Armstrong Energy is building the first commercial-scale CAT-HTR plant for end-of-life plastics. Project partners will take end-of-life plastics and use them as feedstock for the CAT-HTR plant, keeping them out of landfill. And waste producers will pay them to do it.
The fabulous part about this is the raw material is actually a negative cost to us. So I'm taking their product, re-refining it, and selling it back to the same people that are making the plastic bags. So it's a fabulous business model for us because it is just one of these circular economies.
And in Prince George, Canada, North America's largest pulp producer, Canfor Pulp, is using CAT HTR to diversify their revenue.
We're very excited about the potential opportunity here. A few years back, Canfor Pulp did a worldwide inventory of the technologies available, and Licella stood out. So we've now formed a joint venture where we're going to take their CAT HTR technology and fully integrate it into a kraft pulp mill. Our project is going to create renewable crude at a very competitive price to conventional crude. And we're going to have a greater than 80% carbon intensity reduction.
We reduce the impact and it gives them a brand new revenue stream. This is applicable to any kraft pulp mill on the planet. So the exciting thing is, once we've done it with our partner in Prince George, it means we can offer that to the 7,000 pulp mills that exist around the world.
And with biofuel incentives in North America driving strong interest from oil majors, Licella is just beginning a global rollout of the game-changing CAT HTR technology.
Reducing environmental impact, reducing CO2 emissions, and increasing value at the same time.
Licella, a bridge to a lower carbon future.
Thank you very much for that. We can go back to that presentation. Okay, guys. So that gives you a little bit of context of what our company is doing here on the Central Coast. We have piloting facilities in Somersby. We also work very closely with the University of Sydney, like you've seen there, Professor Thomas Marshmeyer and his team. It's been a development process over the last 12 or 13 years. Our real aim is really to divert waste, plastic waste that goes to landfill. We want to have a solution for that. We think we have a solution for that. The waste industry and the plastic waste industry is so large that it can really accommodate a lot of players. There are a lot of plastic on the planet going around. And to give you a little bit of extra context, in 1950, the world produced only about 1.5 million tons of plastic. That is now over 360 million tons of plastic currently. So we are consuming a lot more plastic. Plastic is not necessarily a bad thing. It is a fantastic product. It's light, it's cost effective. It gets used in about everything in your car, in whatever products you have, even in clothing. But we've got to be more responsible on how we manage plastic and the waste of plastic and not just shove it into a hole in the ground. So let me quickly whiz through. I know I've taken up a little bit of time with that presentation, that video. And a lot of things have been mentioned in that video as well. We are really at the forefront of using the CAT HTR technology, hydrothermal liquefaction, as I also refer to it, in the industry. So we are right at the leading pack of that. We process or create a synthetic crude oil that can then be further refined into fuels or other petrochemical products. Even bitumen and the residue that comes out of the distillation column is pretty much bitumen that can be used in road base, etc. Catalytic hydrothermal reactor, that was mentioned in the video as well. That's what it stands for. Development period has been over 13 years and over $90 million have been invested in this over this period of time. So it's a huge amount of investment that flowed into this technology to get it where it is. What we're trying to do also is create a single process that can cater for different types of feedstock, from plastic to biomass in the same sort of process. Now, any process engineer like myself, been in the industry for 20 years, would think that's really a mind-boggling thing, how to get your head around that. You have a process, you change your feedstock, the process is going to change, right? Well, in our process, we are cracking plastics, and if the composition of the plastic changes, because a batch comes in that's got more polyethylene than polystyrene or polypropylene, the process is not going to change that much. your yields at the end, what you can distill, those yields, those fractions will change slightly, but the process will still run. It will still run under the same temperature and pressure conditions, and it will actually still continue the cracking for you. So that's a fabulous part of our technology, is that it's so robust and flexible for different plastic feedstocks. You don't have to go to the nth degree to separate out and get a clean feedstock. It's all about lowering carbon dioxide, and as you've heard, we can achieve an 80% reduction in carbon dioxide emissions and be really a lot more responsible with regards to our global emissions. The Honourable Scott Morrison, our Prime Minister, has mentioned our technology specifically last year at the US General Assembly, where he referred to the catalytic hydrothermal reactor as a very innovative Australian technology, and he gave us that sort of visibility. So we've had a lot of people contacting us, finding out, okay, can we give you our waste plastic? Can you get rid of it? And it's fantastic to have that sort of visibility, and that it gets really recognized and visible at higher levels in politics. How the process works, as it was explained in the video, we have a feedstock coming in, whether that be plastics, we can do biomass, we are looking at doing waste tires even, any type of polymer that doesn't contain too high chlorides and so on. We feed that into our process. We go through a set of reactors where the reactions really happen, and we keep it there for around 20 or 30 minutes. You have an oil coming out. We can then further distill that, and we do have the distillation plant as well in Somersby. So you can have your naphtha fraction coming out, you have your middle distillate diesel fraction, and you have the waxy and the residue fractions coming out of that column. And that's essentially what you get as products then that can be reused for making other chemical products or fuels or bitumen. So the development has been over a period of time. Like I explained, we went through different generations of scaling up, starting in 2007 with a first generation reactor. It was only about, I think, 1 inch in diameter. That got scaled up to about 4 inches in 2011, and then we went up to 12 inches of reactor sizes. So it's been a process, and we have found out over time that it doesn't really have a detrimental effect on product quality at all if you scale it up. So I'll quickly go through this. This is just a comparison between the catalytic hydrothermal process and pyrolysis. For those of you familiar with pyrolysis, pyrolysis is really heating things up in the absence of any air or oxygen, and it forces temperature to actually cleave the polymers. The problem is you get a quite an unstable product. It got a lot of oxygen in it, and that's why it's corrosive and unstable. And that is just what is summarized here. The catalytic hydrothermal reactor oil is about double the energy content of what you will find with pyrolysis. The product is also a lot more stable because you have stabilized it with water. You have actually used water in a process to affect chemical reactions and decarboxylate the acids, and you have a stable product. Just a little bit of an explanation of what the different yields would be for biocrude and plastic crude. For biomass, you would look at about 50% or 60% yield of oil, which could be used for marine fuels applications, and you'll have about 40% higher value carbon products. And we are working with the University of Newcastle, University of Sydney as well, on defining or working more out what we can do with that 40% carbon product. There's very interesting developments going on there, like specialty type foams. There is things like carbon fiber that we've been talking about. Also, the use of that material in arc furnace electrodes is quite an interesting one that the Japanese are really interested in looking into that. So there's a lot of development going on for high value products in that area there. On the side of plastic, you'll get about 80% yield of fuel-related material. That would include the lights, the naphtha kerosene fraction, that can be used for making plastics again, because you can put that through a steam cracker and make ethylene to make polyethylene again, as well as then the fuels and then some residue, wax and bitumen and so on. What we're trying to do is find offtakes for all of those things. We don't want anything to go to landfill, and we don't want residue that you still have to shove into landfill. We can use it all in for different applications. This is just a little bit of a footprint of what's happening with our JVs in Canfor, Canada. That's where we're looking at the biomass project. With Renew ELP in the UK, we have formed an entity called Mura, which is a joint venture between Licella and Armstrong Energy. And Mura actually refers to the Aboriginal name Mura, which means good spirit, or can also be translated into pathways, so as to have that connection to Australia. Now, Mura has got the worldwide license for building these types of plastic plants, except in Australia and New Zealand, where IQ Renew has the license for rolling out these plants. Commercial projects currently happening on our Summersby site. We are changing and again upgrading our pilot facility, probably to a generation 4, but that would be a small commercial scale project or plant to demonstrate the commercial side of it. We are looking at the project in the UK to be commissioning that plant around 2022, if COVID eases. And then for Canada, that's around 22, 23. That's where we're looking at commissioning a plant there. And the size of that plant will be slightly bigger than that for a plastics plant, because the economics makes more sense. Marine fuel application is really a good one that we are interested in from a plastic point of view, because the plastic quality or the fuel quality from plastic derived oil is really good. You don't have to do a lot of refining to it. It basically almost meets the marine specification, marine fuel specification. There's been a big drive by the IMO, International Marine Organization, to drive sulfur levels down. You guys have seen the big passenger ships in Sydney Harbour emitting sulfur, and people are coughing and they got asthma and all of that. Well, so that's going to change, because the sulfur levels are reducing down to 0.5%, or it has already happened as of January this year. So our product is really good because we are ultra low in sulfur. We don't have a lot of sulfur in our crude. Just the marine fuel market, there's really some opportunities there. Like I said, the sulfur, we don't have high NOx and SOx emissions from our product. And there's a big market there. There's over 300 million tons per annum of that fuel that's being used up worldwide. Quickly on the plastics recycling, you've all probably seen this picture or heard about people saying by 2050 there'll be more plastic material in the ocean than fish. And that's a big problem. I don't want to go to a restaurant in 2050 and wonder if I get a plastic fish on my plate, but that's where things are going if we don't change the trend, and we need to change it. We need to become more responsible with plastics and chemically recycling it. So we have formed a JV with Mura, as I explained earlier on, and that will give us a pathway to that commercial plant in the UK for doing 20,000 tons per annum. Just for the technically minded guys around here, this is what you'll see coming out, a distillation column. So the picture on the top there on the left, this is where the lights are, and it sort of works its way to middle distillates. The diesel fraction is around 280 degrees to, or 180 degrees to about 360 degrees boiling point. So a big chunk of that in the middle would be middle distillate or diesel. And then on the right, you'll see some waxy fractions. That would be specialty wax materials and residue that other off-takers are interested in. So what is the supercritical water thing that we've been talking about? Earlier we heard about supercritical CO2. Well, we use supercritical water. It's interesting that people are reverting to supercritical use of materials. It simply means that we are heating up water above its supercritical point, and that is around 373 degrees and 218 bar. Under those conditions, water becomes really interesting because it's neither liquid, it's nor a gas. It's somewhere in between. It's a homogeneous mixture, and it's got a really low density. It's very high in diffusivity. It's acting as an acid as well as a base, because you can easily split off the hydrogen, and it's a very strong solvent. It's like acetone under those conditions, so it really starts dissolving plastics and ripping things apart. The picture there just shows what I've been talking about. On the left upper corner, this is where you find a clear meniscus between the liquid water level and the vapor above it. As you heat it up, it becomes cloudier, and at the bottom here, on the right at the bottom, that has completely disappeared. So you're now sitting with a mixture that's been completely heated up and homogenized and acts as a solvent as well as a base. The other properties, interesting properties, or benefits that we have from the process is a very high conversion efficiency. There's about 85% conversion yield from our process. The balance would basically be gas, and that gas can be recycled back into the process by firing your boiler, or if you are setting it up on a refinery, that gas will further be used in a steam cracker to actually make new plastic. The process is very easily scalable because of the fact that the heating is so efficient. We don't necessarily have to put in external heat and try to get it through a pipe to heat things up. We actually have it in the water that we inject directly into the stream. So you get direct heating from that process. It produces a higher yield from other processes like pyrolysis, for example. The process is also tunable, so we can tune it whether we want to make a fuel or we want to make more of a chemical waxy product, depending on who your off-taker is and what they want, which is really great. We don't produce toxic compounds, and the products are actually REACH registered in the UK and in Europe. What that means is simply that REACH is an organization, it's a chemical organization in the UK. It's a body, it's an independent body that requires registration if you're going to sell or make any chemical products. So it will tick all those boxes as being safe for consumption. As I said, we teamed up with IQ Renew. IQ Renew used to be Stop Waste in the past. We formed a joint venture with them to form IQ Renew. They operate material recycling facilities in Somersby as well as in Wyong, and they collect all the yellow bins all the way from the North Shore up to the upper Central Coast, goes to their facility. So it gives us that assurance that we have feedstock for our process, and that's great because it's all now consolidated to a single point. This is just a team. Dr. Len Humphries, you saw him in a video, and Thomas Marshmeyer, they were really the inventors of this technology. It's been developed over 13 years or so. The last 3 years, I've been working very hard in developing this for plastics, and my team, we got about 10 engineers on it, chemical, process, mechanical, control, instrumentation, whole range of engineers, and we have got it to a point where it can actually be commercialized now. And I think that's pretty much it. Am I hitting the time? Yeah? Okay, so it might be a minute or two for any questions.